Hi, today I'm doing October, November 2019 paper 4 so let's go. First question, a crane is lifting a load of 1,250 kilograms vertically at a constant speed of V. Okay. Um, Given that the power of the crane is constant at 20 kilowatts, find the value of V. Okay, so the power is equal to the force times the velocity. So the power given is 20,000 watts. You had to convert it into the SI unit. So you need to convert it into watts, not leaving it in the kilowatt form. And the force is the weight, and weight is equal to mass times gravity. So that would be 1,250 times 10 and times the V. So V ends up being 1.6 meters per second. Question 2. So the total mass of a cyclist and her bicycle is 75 kilograms. The cyclist ascends a straight hill of length 0.7 kilometers, inclined at 1.5 degrees to the horizontal. The speed at the bottom is 10 meters per second, at the top is 5, and the resistance to motion as the cyclist ascends the hill is 2,000 joules. The cyclist exerts a force in the direction of their motion. Okay, so we need to find this force. So basically, it's an inclined plane with an angle of 1.5 degrees, and the cyclist travels a total of 700 meters. Yeah. So first, let's calculate the loss in kinetic energy. So loss in KE, that's equal to half m u squared minus v squared. So that would be half 75, 10 squared minus 5 squared, and that gives you 2,812.5 joules. And so now we have a loss in kinetic energy. Now let's calculate our gain in gravitational potential energy. Formula for gravitational potential energy is mgh. So the mass is 75, and acceleration to gravity is 10, and the height is going to be the vertical component in this diagram. So it's going to be 700 sine 1.5. So that's going to be 13,743 joules. Now we need to form an energy equation, and we need to represent the work done by the driving force, the work done by the driving force with a variable. So I'm just going to represent it like this. And in order to form our energy equation, we need to realize where energy is being lost and where energy is like being gained, what is being transformed to. So when the cyclist loses kinetic energy, as I said, it just loses the energy. So the energy has to be transformed to another form by law of conservation of energy. So the same applies for the work done by the driving force. It needs to be converted into another form. So those two will be on the same side of our energy equation, because they are both like donating energy, transforming energy to other forms. And the other forms that the energy is transformed into are gravitational potential energy, as there's a gain, and the work done against the resistance. So basically, this is your energy equation. Yeah. When you plug in your values, you get and you evaluate, you get your work done against the your work done by the driving force will be 12,930 joules. Okay, and we know that work is equal to force times distance. So if we want to get the force they asked us for, we need to divide our work by the distance. So we divide 12,930 by the distance moved, which was 700, and we get 18.5 newtons. So therefore, F is equal to 18.5. Okay, next question. A block of mass 3 kilograms is at rest on a rough plane inclined at 60 degrees to the horizontal. A force of magnitude 15 newtons acting up a line of greater slope of the plane is just sufficient to prevent the block from sliding down. So that means that the block is about to move down the plane, so the friction acts up the plane. So okay, let me give a visual representation. So this is the box. This is the 15 Newton force. This is the resistive force. The length doesn't matter. I just drew it longer. And this is the weight component down the slope, which is mg sine theta. So basically, it's just about to move down the plane. So that means there's an equilibrium. So the resultant force is 0. So the forces going up are equal to the forces going down. So you get this equation. And when you plug in your values, you get 15 root 3 for this. And so your resistive force is 15 root 3 minus 15, which is equal to 10.98. Basically, from this part to this part, I just put in the mass, which was 3 kilograms, gravity 10, and sine of 60. So that's how I got 15 root 3. So now that we've done that, we also know that the resistive force is equal to mu r. This is the formula. And we don't know what r is yet, so we need to calculate that. R is actually equal to mg cos theta, so that will be equal to 3 times 10 times cos 60 degrees. So R is equal to 15 newtons. So now that we have R and we have our resistive force, we can just plug them into the equation. So 10.98 is equal to mu times 15. So mu is equal to 0.732 as our final answer. Okay, so in the second part, they are saying that the force of magnitude 15 newtons is replaced by a force of magnitude x acting up the greatest sine of slope, and we need to find the greatest value of x for which the block does not move. Okay, so now x is larger, so that means that the block is about to move up in this case. So x is like here, and since it's bigger, the friction will adjust, so it will move to the other side. It's trying to prevent the block from moving up this time instead of preventing it from moving down. So the friction acts downwards. Mg sine theta always acts downwards. So this is the diagram. So basically, you just form a force equation from this, just like you did for the previous question. So X max is mg sine theta plus the resistive force. So 30 sine 60 plus 0.732 times 15, which is 10.98. So basically, X max is 37.0 newtons. All right, next question. Question 4. Two blocks A and B of masses 4 and 5 kilograms respectively are joined by a light and extensible string. The blocks rest on a smooth surface inclined at angle is that alpha, yeah, alpha to the horizontal, where tan alpha is equal to 7 over 24. The string is parallel to a line of greater slope with B above A. Okay. And a force of magnitude 36 newtons acts on B. Okay. Okay. So I think there's multiple ways to do this to find the acceleration of the blocks and the tension in the string, but this is the method I am most familiar with. You can resolve individually. So you can resolve the forces acting on block B and block A, and you get two simultaneous equations which you solve to get each of the variables we are looking for. So on block B, we have a 36 Newton force. So 36, I'm going to take upwards as a positive direction. And 5 sine alpha is acting down because the weight of block B is acting down. So 5 sine alpha is acting down, trying to prevent it from moving. And the tension in the string is also trying to prevent it from moving up. So we get 36 minus 5g sine alpha, because you need to add you need to multiply by the acceleration due to gravity. So 5g sine alpha. So when you put these in the equation, you get this, and is equal to, there's no equilibrium here, so there's some acceleration. So it's equal to the mass times the acceleration, the resultant force. In this case, our mass of B is 5, and acceleration is unknown, so we just represent it with A. So this is your first equation, but there are 3 unknowns. However, we can solve for alpha since we already know that tan alpha is equal to 7 over 24. So alpha is equal to tan inverse of 7 over 24. So alpha is equal to 16.26 degrees. So now we have 36 minus 50 sine 16.26 minus t is equal to 5a. So if we evaluate that, sine 16.26 is 7 over 25. So basically we'll get 36 minus 14 minus t is equal to 5a. So 22 minus t is equal to 5a. That's your first equation. Then the next equation, we need to resolve the forces on A. And these are actually only 2. Just the tension in the string, which acts in the opposite direction this time. So the tension is acting up. And the weight of the block itself, the component down the slope. So mg sine alpha, I wrote that horribly. Mg sine alpha is acting down the slope. So basically, it was going to be, if we consider the tension to be acting in the positive direction as we did for block B, it would be T minus 4g sine alpha is equal to 4a, since the mass of the block is 4 this time, not 5. Okay, so in this case, we'll get T minus 11.2 is equal to 4a. Yeah. So that's your second equation. I can rearrange this to get T is equal to 4a plus 11.2. And I can rearrange the first equation to get T is equal to 22 minus 5a. So now if we combine those, since T appears in both, we can just substitute it in. So we get this equation. and you just solve this equation in order to get the value of a. So 10.8 is equal to 9a. Therefore, a is equal to 1.2 meters per second squared. And now just substitute this value of a into your any of your t equations, doesn't matter which one. If you've done it correctly, you should get the same thing. So basically, t is equal to 16 newtons exactly. Okay, so the second part, at a particular instant, the speed of the blocks is 1 meters per second. Find the time after this instant that it takes for the blocks to travel 0.65 meters. Okay, I think you apply the Suvat equations here. The initial speed is 1 meters per second, 1 meter per second. The acceleration we calculated earlier, so it depends on your answer from the previous part. So if you got the first part wrong, you get this part wrong. So the acceleration is 1.2, and the distance we are moving is 0.65. Okay, so we're finding time. We have distance or displacement, acceleration, and initial speed. We can use s is equal to ut plus half at squared. So 0.65 is equal to t plus 0.6t squared. And basically, you rearrange this. It's a quadratic equation. You can rearrange it, complete the square, or use the quadratic formula. I personally prefer to use the quadratic formula. So that's what I'm going to do. What am I doing? So this is your quadratic equation. 0.6t squared plus t minus 0.65 is equal to 0. So basically, I'm just going to use the quadratic formula. When you do this, you'll get t is equal to 0.5 seconds and t is equal to negative 2.17 seconds. Now time can be negative, so therefore t is equal to 0.5 seconds. Okay, so now we have a small ring P threaded on a fixed smooth horizontal rod AB. Three horizontal forces of magnitudes 4.5, 7.5, and F act on P. Given that the forces are in equilibrium, find the values of F and theta. Okay, so for this question, we need to resolve the forces horizontally, equate them to 0. Resolve the forces vertically, equate them to 0, and we'll get a simultaneous equation which you can solve to get you get simultaneous equations, that you can solve to get your F and your theta. So for the x direction, okay, so F cos theta minus, these are all acting in the opposite direction, so minus 4.5 cos 20 degrees minus 7.5 cos 60 degrees is equal to 0. So I can move these to the other side and simplify, so I get my F cos theta is equal to 7.98. Now for the vertical direction, so F sine theta 4.5 sine 20 minus 7.5 sine 60 because it's acting downward. Well, my pen is bugging out. So when you rearrange and simplify, you get f sine theta is equal to 4.96. This is a simultaneous equation which you can divide the first one by the second one in order to get tan and eliminate f. So we can do that. So we get tan theta is equal to 0.621. Theta is equal to the tan inverse of that. So therefore it's equal to 31.8 degrees. And now we can sub that into any one of our equations. So f cos 31.8 degrees is equal to 7.98. And we get ourselves F is equal to 9.39 newtons. Okay, so the second part, it says that instead the values of F and theta are 9.5 and 30 respectively, and the acceleration of the ring is 1.5 meters per second. Find its mass. Okay, so there can't be vertical acceleration because it's fixed to the rod. So we're going to have to do resolving the forces horizontally to find the resultant force and using that to get the mass. So that would be F cos theta, which is 9.5 cos 30 degrees minus 4.5 cos 20 degrees minus 7.5 cos 60 degrees. That's the force in the x direction, or the resultant force. So you get a resultant force of 0.249 newtons, and since this is the resultant force, is equal to the mass times the acceleration, and the acceleration they gave us to be 1.5 meters per second. So we just plug that into the equation. And we get our mass to be 0.166 kilograms. Okay, next question. A particle of mass 0.4 kilograms released from rest from a height 1.8 meters above the surface of water in a tank. Okay. There's no instantaneous change in speed when the particle enters the water, and the water exerts an upward force of 5.6 newtons on the particle when it's in the water. So first part says we should calculate the velocity at the instant it reaches the surface of the water. So basically the mass is here. It falls a height of 1.8 meters. See, the water is here. Yeah, it falls a height of 1.8 meters and it's a rise. So the initial speed is 0, the distance is 1.8, the acceleration is 10. So we can just use v squared is equal to u squared plus 2as. And we get v squared is 36, so v is 6 meters per second. Next, find the time that it takes from the instant when the particle enters the water until it comes to instantaneous rest in the water. Okay, and you may assume the tank is deep enough so that the particle does not reach the bottom. Okay, so first we need to calculate the weight of the particle so that we know the downward force on the particle. And the weight is equal to mass times gravity, which is equal to 0.4 times 10. So the weight is 4 newtons. And they told us that the resistive force is constant and is 5.6 Newton. Right. Okay. So with this information, we can calculate the resultant force. So 5.6 minus 4 is equal to 1.6 Newton. But you have to keep in mind that this force is acting upwards, since the resistive force is acting upwards as the particle travels down through the water. So now that we have our resistive force, we can find the acceleration of the particle. So acceleration is equal to force divided by mass, and the force is 1.6 and the mass is 0.4. So we get 4 meters per second squared as our acceleration. Okay, so the initial speed of the particle falling through the water was 6 meters per second, because that's what we calculated in the first part. It entered the water with this speed. So the final speed, the speed we're trying to study, the time it takes to reach the speed. So the final speed is 0, and our acceleration is actually negative 4 meters per second, because the acceleration is upwards and the speed is downwards, so it has to act in an opposite direction. So v is equal to u plus 80 is sufficient for this, and 0 is equal to 6 minus 4t. So 4t is equal to 6, so t is equal to 1.5 seconds. Next, sketch a velocity time graph for the motion of the particle from the instant it is released until it comes to instantaneous rest in the water. Okay, so we know, let me draw my axis. Okay, so let me label the axes. Velocity, okay, so let me label the axes. This is velocity in meters per second and time in seconds. So we know that the particle travels outside of the water, falls a distance of 1.8 meters, and then lands in the water. And then that's when the acceleration changes direction. So first it's falling due to gravity, and then it starts to accelerate in the opposite direction. So the velocity in the initial direction starts to decrease. So first we need to find the time it took to fall from its height of 1.8 meters above the surface of the water. So we have the final speed, we had the initial speed, and we have the acceleration, which is 10. So 10t is equal to 6, t is equal to 0.6. This is the equation I used, by the way. V is equal to u plus 80. Final speed was 6, initial speed was 0, and acceleration was 10. So 0.6 is when it hits the water. So that means we need to put something at 0.6. And the other section lasted 1.5 seconds as we calculated. So if you add 1.5 to 0.6, we get 2.1. So that will be another major point. Basically, it's just constant acceleration of the particle from t is equal to 0 to t is equal to 0.6, and it reaches a speed of 6 meters per second. So we can mark 6 and then draw a line there. Okay, and it basically just accelerates constantly in the opposite direction. So same straight line with a constant gradient from velocity is equal to 620 in 1.5 seconds. So basically, I did not draw that well at all. Pretend it's a straight line. Pretend it's touching. Okay, you get the idea. So next question. Particle moves in a straight line starting from rest at a point O and then comes to instantaneous rest at a point P. Okay, and they've provided the velocity equation. Show that the distance OP is 6.25 meters. So basically, what we can do is, first we have to equate it to 0 because they said that it comes to instantaneous rest at the point P. So equate this to 0 and solve it. Here we can factorize t out because the t is equal to 0, solution is not needed. So t is equal to 5 seconds. Now all we need to do to get the distance is integrate the original equation with the limits 5 and 0. With respect to t. So if I just integrate with no limits, if I just do this, I'll get 0.6 t cubed divided by 3 minus 0.12 t to the 4 divided by 4 plus c. So 0.2 t cubed minus 0.03 t to the power 4 plus c. So in this case, we just applied the limits. Five and 0. We apply the limits. And when you do that, you get something like this. The 0 part doesn't add up to anything because constant multiplied by 0 will still be 0. I'm running out of space. Yeah, so basically you get OP is equal to 6.25 when you put it in a calculator. Next question. On another occasion, the particle also moves in the same straight line. On this occasion, the displacement of the particle at time t seconds after leaving from O is s meters, where s is equal to kt cubed plus ct to the power 5. Okay. Given that the particle passes point P with velocity 1.25 meters per second at time t is equal to 5, find the constants k and c. Okay. So we already know that the distance OP is 6.25 meters. So we can put that in. And it occurs at time t is equal to 5, as they said in the question. So this is our first equation. So 6.25 is equal to 125k plus 3125c. That's our first equation. And now we need to make use of the velocity they gave us. So v is equal to ds dt. When you differentiate displacement with respect to time, you get velocity. So that would be 3k t to the power 2 plus 5c t to the power 4. And they said at the point P, the velocity is 1.25 meters per second. And that's, yeah, times 5. So just put those into the equation. You get 1.25 is equal to 75k plus 3125c. So this is your second equation. As you can see, 3125c appears twice, so I can make it the subject and then substitute it into the previous equation. So I get 6.25 is equal to 125k plus 1.25 minus 75k. Okay, so I get 5 is equal to 50k. So k is therefore equal to 0.1. And I just plug that into any one of the equations before. So c is equal to negative 2 times 10 to the power negative 3. Okay, next. Find the acceleration of the particle at time t is equal to 5. So we have the constants. We have the constants now. We have a velocity equation already. If we differentiate the velocity with respect to time, we get acceleration. So that would be 6kt plus 20 ct to the power 3. Now if we put the values we just found into it, we get 0.6t minus 0.04t to the power 3. Yeah, that's it. That's your acceleration equation. So now all we need to do is plug in time t is equal to 5 and see what results we get. And the answer is minus 2 meters per second squared. Oh, that's all. I thought there was more. Anyway, thank you for watching.